Okay, so welcome back from the short break that we got. We go now straight to the end of the semester. Please mute your microphones so there's no background noise. Thank you. Um, we are in class number 7. Today, the daily quiz is quiz number 7, which is sort of a recap of some of the problems you've already seen before, just to make sure that the averages go up and all the students are able to understand those core ideas. So daily quiz 7 due tonight. Please go ahead and answer those questions on Gradescope. Today is Tuesday, Feb 16th. Homework. Homework 3 is due tonight on Gradescope. Please make sure you submit that. This is individual work. The next homework, which is a lot of good practice about Boolean algebra properties and how to use them, how to use them to verify certain equations, how to use them to simplify certain equations. All of that is in homework 4, which has been posted on Piazza and is due on Gradescope next Tuesday. So Tuesday, Feb 23rd. Studio, finally, Studio 1 is due tomorrow. So make sure that you do two things. One, TA checkoff, as well as the studio report on Gradescope. Both are required for studio submissions to be valid. Studio 2, you guys are continuing to work on this. It's due Feb 24th, so you have a few more, just over a week to complete Studio 2. Exam 1 is actually coming up next week, so I will be posting some back exams, some topics, some helpful material regarding exam 1 soon, sometime tomorrow. So keep an eye out on Piazza under resources to do this. Yeah, quiz 7 is repeat. Essentially, I've given problems that did not have a very impressive average. So I accumulated those. All right, let's see. A few questions. Can we do the checkoff tomorrow in studio? You can do checkoff anytime you want when the TAs or undergraduate student assistants are available. And because Studio 1 is individual assessment, you don't even have to wait for your partner to go into the studio set to get checked off. Is Studio 3 going to be released this week? Yes, I will be releasing Studio 3 after we get done with Studio 1. So sometime Thursday maybe I will post Studio 3. But it's a little bit more complicated studio, so you will have some time to work on that. Okay, which lectures will exam 1 cover up to? So wherever we stop is what will be on the exam. So I will have a little bit more clarity about which lectures on Friday. Let's see. But in general, you should expect things that are covered before the exam to be on the exam. Details to follow. All right, let's get into Boolean algebra properties that we have been working on. So we have been looking at properties that were one variable and two variable Boolean algebra laws or theorems. And we have looked at essentially three different ways of proving them, right? So one was perfect induction or the truth table method, which seemed to be pretty straightforward. The other was using Venn diagrams, which is also very straightforward and a graphical representation of Boolean properties. And the third one we just introduced was the way to prove Boolean algebra properties using other Boolean algebra properties. So those are the three ways we have looked at, and we have completed about 11D. And now we are going into DeMorgan's law, which is one of the very famous Boolean algebra properties you will come across, right? So 12 and 12D are duals of each other. Let's take a look. Now, when you look at DeMorgan's law in general, it says this is of any number of variables, right? Some finite number of variables, X, Y, Z, and so on. And what you're doing them on the left-hand side is you're ORing all the variables, and then you're complementing the entire odd sum. And DeMorgan's law says that is the same thing as inverting each of these variables and then doing an AND operation between them. So if you just look at the two variable equivalent of 12, it would look something like this. You would have X or Y, the whole thing gets complemented, right? So I'm going to zoom in over here and I'm going to start sketching. So X or Y OR gate between them, right? This is X, this is Y. So the left-hand side says, if you do OR first and then complement the result, which would be a bubble at the front there, this is equivalent to inverting the variables first and then going through an AND gate. So over here, what you have X or Y, the whole thing is complemented. And on the right-hand side, what do you have? You have X complement ANDed with Y complement, right? So that's DeMorgan's law. Again, you can use truth table method to prove this, or you can use Venn diagrams way to prove this. We are not going to look at a lot of proofs. I'll save the proofs just for the slightly more difficult problems for today. But that's it, right? So that's your DeMorgan's law. And one way of looking at this is that bubbles, when they push through an AND gate to go to the outside, they convert that AND gate to an OR gate, right? So, think of it in terms of bubbles pushing through a logic symbol, and as they go to the other side, they convert the AND to OR, and similarly, you will see that it also works the other way, OR to AND, and so on. So that's your two variable equivalent. Now, one thing that, kind of gets missed is this. The question is this going to be the same as this? What do you guys think? Is it equal? Is it not equal? Oh, well, it cannot depend. I'm afraid it cannot depend, right? Either it's equal or it's not. So even if it breaks for one of the conditions, it breaks. Right, so it's not equal, right? So that's one of the things that gets there is confusion about this. This is actually not equal, and you can actually make a truth table, have a column for X, have a column for Y, have a column for X complement and Y complement, and then have a last column for X NAND Y. You will see that these two columns do not match for all the four entries in the table, which makes it not equal, right? So that's again to the point that the way you write this, the bar over the X and the bar over the Y, a clear depiction of the logic expression is pretty important, because if you did not break this up in the middle and you wrote it like that, it would not be the same logic expression. Okay, now let's look at 12D, which is the dual of 12, meaning we are replacing ANDs with ORs, ORs with ANDs, ones with zeros, zeros with ones, right? So what does that look like? Well, you have X and Y and Z, the whole thing ANDed, and then you are taking the complement of that. Is going to equal X complement or Y complement or Z complement and so on, right? Exactly the dual of 12. So over here, we essentially have, instead of OR, we have AND on the left-hand side, and instead of AND, we have OR on the right-hand side. That's the only difference. So let me write this expression for two variables' sake so that you guys can see this. You have X and Y, and the entire thing gets complemented, equals you have X complement or Y complement. That's your two variable equivalent, right? So two variable version. And you can see this is not the same as this, right? So clearly our not equal sign over here is appropriate. So those are the two DeMorgan's law. One is the dual of the other. And these are essentially, related to NAND operations and NOR operations, and what they equal to. So in one case, you NAND them first. In the other case, you invert them first and then go through an OR gate, right? The same thing applies even for 12D. Now, let's take a look at 13. 13 is a very general representation of DeMorgan's law. And it also kind of borrows a few things from other things that we have learned. So this is a general representation. 13. And it's not the same thing as finding the dual of an expression. Let's take a look. Because when we said dual, we explicitly mentioned that we cannot change or complement the literals in the expression, right? We mentioned that. So over here, you will see in 13 that you actually have to invert the variables as well, the literals as well. So what do you have on the left-hand side? You have a certain function, f, logic function f, which is dependent on x1, x2, and so on up to n. Those are n binary input variables. And there are some zeros involved, one involved, there's an OR operation, there's an AND operation, but all of that function on the left-hand side is complemented. And on the right-hand side, it says it is equal to applying the same logic function, but instead of x, you are replacing that with x1 complement. Instead of x2, x2 complement. So you're complementing all the literals. You are changing the zeros to ones, ones to zeros, ORs to ANDs, ANDs to ORs. So the only difference is on the left-hand side, you apply the function, then complement it. On the right-hand side, you simply apply the function on everything that has been inverted. Everything. ORs, ANDs, ones, zeros, literals, everything. So that's your general representation of DeMorgan's law. Let's move on to so we are 16 and 17. These are multiplying and factoring theorems. So let's take a look. Now we are in the world of three variable properties here. So the first one is x or y ANDed with x complement or z, and then it says it's equal to x and z or x complement and y. So let's go ahead and prove this one after squared. So this one is my 16, and we are going to say my x or y ANDed with x complement or z, and the property says this equals x and z or x complement or y, right? So like we said, we can start with the left hand side and try to manipulate the expression so that we go to the right hand side, or we can do it the other way. In this case, I know that I can distribute this using FOIL very quickly. So I'm going to start with left hand side and try to manipulate things using some of the tricks that I learned at the end of last lecture. So we'll revise those so that we go to the right hand side. I'm going to do the proof here. Left hand side, again, we are using Boolean algebra properties here. I'm going to start with left, and I'm going to use FOIL, right? So if I do that, I have x and x complement, or x and z, or x complement and y, or y and z, right? And I can clearly see that this guy equals 0, so I don't need to worry about that. Now what do I have? I am left with x and z, or x complement and y, or y and z. Now I'm going to take a moment here to recognize what is the difference between my current left hand side and my right hand side. It looks like y and z over here is missing, right? But other two are there exactly in the same manner. X and z, x and z, x complement and y, x complement and y, right? So I need to do something to this left hand side without changing it logically, right? I cannot mess with the logic. It needs to be logically equivalent, meaning the truth table of the function should not change. And I need to find a way to essentially eliminate this term y and z, right? So again, we are going to borrow some of our tricks that we learned last time. Over here, what we are going to use is, I'm going to force the missing literal on the term that needs to be eliminated. So what should I force on this particular term, y and z? What literal is missing from there? If both x and y are true, one of the first two statements will be true anyway, so y and z is redundant. Yeah, that's right. Yeah, your statement is absolutely valid. We are just trying to validate that with a proof. Now, so let me come back to this. What literal is missing in y and z? Note that this particular statement here, 16, is dependent on 3 variables, x, y, and z, right? So y and z, that particular product term is missing x. So what I'm going to do is I'm going to force that missing literal by doing a simple manipulation to this, which is I'm going to leave x and z as is. I'm going to leave x complement and y as is, and I'm going to AND this with the missing literal without changing the value logically, right? So I've essentially ANDed this y and z term with x or x complement, which is always going to be true. And something ANDed with true is always going to be the same variable, right? So y and z and 1 is the same as y and z. Now that I've done that, I can expand this x and z, x complement and y. I've got what, x and y and z, or x complement and y and z, right? So that's where I am at in terms of expanding things up. Now I have it in a very consistent expression, right? I have a product here, product here, product here, product here, and everything is getting ORed, O-R-E-D, ORed, right? So this is what we are going to call a sum of products expression, right? So product, 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 and all the products are getting summed, not arithmetically, but logically, right? So that's a logical OR operation. Now what I can do is I can try to figure out whether I can combine certain things with certain other things, right? So it looks like x and z can easily be combined with x and y and z. And x complement and y can be combined with x complement and y and z. So what's going to happen here? If I pull out x and z, I have 1 or y. That's for the yellow terms. And then I've got x complement and y. And then I've got 1 or z here, right? So true or anything is true. So make that into blue, make that into yellow, and this tells me that this is going to equal x and z, or x complement and y, which is my right hand side. So that proves that. Okay, so Andrew, so Alex is saying that if both y and z are true, one of the first two statements will be true, right? So the only way this term actually matters is because it's in the sum of products expression. We need to look at, is this going to be a 1 or a 0? Because if it is 1, then it changes the entire thing to 1. If it is 0, then it doesn't change it anyway, right? So if y and z both are true, then this becomes 1, but you can also see that this and this will also be 1 anyway, right? Because over here, z is with x and y is with x complement. So no matter which value x has, could either be a 0 or be a 1, right? So whichever it is, one of these terms is going to be a 1 in that case, right? You see that? So y and z is redundant. Actually, you know, when we start looking at glitches and hazards, we are going to call this term exactly that, redundant prime implicant. So this is a little bit ahead here, but this is redundant prime implicant. So we don't need to worry about that terminology just yet, but that's what it is. It is redundant because the only thing I need to worry about is when y and z are 1, right? Because if either is 0, this will go to 0, and I don't have any change in my logic expression. Only when y and z are 1, that's when this is going to matter. It's going to make the entire expression true. And if y and z are 1, it appears here and it appears here. Once with x, once with x complement. So no matter what x is, one of them will be true. All right, so I hope that answered that question. Let us write a couple of statements here regarding some manipulation tricks, right? So manipulation tricks that we have been looking at is, the first one is ANDing. I'm going to make this logic operation into a verb. ANDing with logic 1 or true doesn't change a product term. Right? X and Z and 1. That's what they named the school after. I don't think so, but sure. Let's believe that for now. ORing with logic 0. So when you are adding a 0 in arithmetic algebra, it doesn't change the value, right? Similarly, we can OR with the logic 0, and we can make that OR 0 as simply as X and X complement. That's our 0, right? And over here it would be X or X complement. That's our 1, right? Bit masking, yeah. That's exactly what this is. Let's see. Now we have done this. Let's see. Let's go back to our list here. So we looked at 16, and if you go through 16D, again, it's the dual of 16. So you can, my strategy here, if I was doing this, would be start from here, distribute, try to manipulate so that you go to the left hand side, right? So that would be my way of doing it. Again, there are others who would probably OR this with a 0, logic 0, and try to do it that way. So there are many ways of proving these Boolean algebra properties using other Boolean algebra properties. Let's see. The consensus theorem, 17. So we have X and Y, Y and Z, X and Z, X complement and Z equals X and Y or X complement and Z, right? So if you look at 17 and you go back and take a look at, let's what do we do here? Actually, this is what we proved right now, didn't we? Right, 17 is what we proved right now. When we went from here to here, that's what we proved. Right? This is our left hand side for 17, and this is our right hand side for 17. Right? X and Y, Y and Z, X complement and Z, right? So the X appears here, X complement appears here, Y and Z was our redundant prime implicant, right? It was the term that we wanted to get rid of, and we did. See? So proof of 16 kind of already has proof of 17. And as you know, if you look at 17D, this is the dual of 17. One way of doing this would be, how would you do 17D? I think the easiest way to do 17D would be distribute everything on everything, and then distribute everything on everything, simplify, and make sure that they are the same, right? So distribute. When you distribute this, how many terms are you going to have? Results in how many product terms? Will it be 8? So 2 with 2 will give me 4, right? So 4 with 2 will give me 4 plus 4, 8. And some of them may cancel out, right? For example, X with X complement may cancel out. So some of them will cancel out. And on the right hand side, you will have the same thing. When you distribute, you will end up with 4 product terms here. And if you simplify this, you can try to see if that is equal to that or not. So it's pretty straightforward. You're just distributing things, simplifying them, not in a very, it's not going to be pretty, it's difficult to simplify. The simplification step will involve something like this. X and X complement goes to 0, something as simple as that. And then eventually you will have some terms here, and if you match them, they should be the same. So I'm pretty confident that you guys will be able to do this later on by yourself. And if not, you guys can ask me questions about how to go about doing this. All right, now, how do you get better at Boolean algebra? Well, the more you practice, the better you get, right? Something very similar to what you've been hearing in all your math classes. The more varieties you see, the more comfortable you get, right? The goal is you have a set of properties at your disposal. The question is not whether you remember them or not. The question is whether you can apply them at the correct places or not. So we are going to use some 3 examples here to work out some problems using Boolean algebra properties, and then the homework that has been assigned should really help you, get to the next level, right? To like gain some more confidence in this. Now, the one thing that I want to note before I get into this is when you're using Boolean algebra, the simplest, so the first one we are doing is simplify the expression, right? So the simplest form of the expression sometimes is not very clear to identify, right? So if you have 2 variables, sure, it might be very easy. 3, slightly more difficult. 4, slightly more difficult. So as the number of variables increase in your logic expression, it becomes that much more difficult to identify whether or not the expression is in its simplest form. Now, and to make things worse, Boolean algebra simplification or Boolean algebra manipulation doesn't have a very systematic way to tell you, yeah, you have reached the simplest answer. It's not there, right? So you can check, you can do some checking, visually to see whether it is the simplest or not, but there's no systematic way to do this or identify the simplest form, which is why when we go on and start talking about Karnaugh maps, K-maps, and I will show you the connection between Boolean algebra and K-maps, my goal will be to lead you to a place where even though you are working in Boolean algebra, you should be a little bit more confident in claiming whether it's the simplest solution or not. But that can only happen with the guidance of a K-map. All right, so let's come back to this. We are doing a simplification here. We have an expression there, we have verification problem here, and then we are going to simplify this expression over here. Now, in order to help us, the problem itself says the result only has 3 literals. Let's see if we are able to get that. And for the last one, the result only has 2 literals. So let's do this. Let me add a page after. Go back. We have a function here. Take screenshot, sure, copy, come here, paste it. All right, so that's something that we are trying to prove here, and I'll prove that in red. Now, the first thing I want to tell you guys about this is the longer complement signs I see, I actually feel better about that, because this is a very clear indication that DeMorgan's law can be quickly applied and it will simplify the expression pretty easily, right? So the longer the complement sign and the more number I have, I'm gonna look at this as an advantage rather than as more complication. So let's see. I'm gonna start with my expression here. I need to just simplify. So I'm gonna take this and I'm going to do the first step right away. I'm going to use DeMorgan's law first. And the goal of the reason why I want to use DeMorgan's law is to get rid of that complement sign, the whole thing being complemented, right? So I have f equals, so when I do that, I'm going to treat this as one variable and I'm going to treat this as another variable. So I have a DeMorgan's law in which I have some variable or some other variable and the whole thing is complemented, right? So this is a NOR operation, but instead of having, simple variables, now you have a smaller expression representing those inputs to the NOR gate. So what is this going to equal? I'm going to say it equals x or y complement. This gets complemented. The OR goes to AND, and then the other term here, sorry, I have x or z complement, that also gets complemented, right? So I'm going to use the parentheses to make sure that I don't spoil the order here. Now, you see what happened here? X or y complement, that was here. This got complemented or changed to AND. This got complemented as well. Now, what happens to the double complement? Double negation cancels out. We know that from property number 4, right? So this is simply going to be what? This is going to equal x or y ANDed with x or z. Now, what is the problem here? The problem over here is this guy has, this is not in its simplest form. It doesn't have just 2 literals. So what am I going to do? I'm going to try to expand this. I'm going to distribute it. When I distribute it, I'm going to have x and x, x and z, x and y, y and z. And this is now going to simplify pretty quick because the first term is x, and that x is going to be my savior because it is present over there and it is present over there, right? So I can pull out that as a common factor between the first 3 terms to get a 1 or logic 1 for the first one, right? I've got z here or y here and then y and z at the end. Now, all of this simplifies to 1. 1 or blank or blank. No matter what those blanks are, it's going to be 1. So what do I have? I have x ANDed with 1, which is x, or y and z, right? Now you see, this is a 3 variable expression, but visually when I look at it, there is an x and there is a term y and z, right? So there is not much I can do. So visually, in some cases, you will be able to claim that it is in its simplest form. And right now it is. It has 3 literals, right? X, y, and z. Those are your 3 literals. So that's your final answer in this particular example. All right, let's go back here and try to look at the second one. We have verify the equation. We are going to take this and we are going to verify this. Again, I have a lot of complement signs going over things. All right, thank you, Kang. I'm going to try to do things a little bit better now. You have put some pressure on me now. So is something simplified when each literal only appears once? Is something simplified when each literal only appears once? In a product term or in a sum term, yes. Right? If you have a product term which has x and x complement and y, well, that is 0, right? So sometimes you might reduce the number of literals in each term, or because you have the complemented version and the true version of the same variable into a product term, it might cancel out altogether. Now, let's come back to B here. Hold up. All right, so let's come back to B here. Again, I have this bar sign over my left-hand side, which makes me feel pretty good because I'm going to be able to use DeMorgan's law. And, a quick check about B is this guy is what gate? Let me highlight this in yellow. What is this guy? Maybe. What logic function is that without the bar? Exclusive OR, right? So exclusive OR complemented equals exclusive NOR, right? Of course, that's how exclusive NOR operation is defined. So I know that this is something that should be okay. We should be able to verify this. And right now, visually, I'm able to make sense out of this. Let's try to use Boolean algebra properties to prove it too. Let's go ahead and add one more page here. And for this, I don't need to copy because I remember what that is. It was B, and it was exclusive OR, so X and Y complement, or X complement and Y. The whole thing gets complemented. And that should equal exclusive NOR, which is X and Y, or X complement and Y complement, right? Okay, so let's see if this is equal or not. I'm going to start with my left-hand side in this case, and I'm going to straight away use DeMorgan's law, right? When I use DeMorgan's law, what do I have? X and Y complement. This guy gets complemented, or turns to and then I'm left with the other guy complemented. Now, it looks like I can, and you can always add parentheses here to help you stay separate in terms of ANDing products or ORing products. Now what we can do is apply DeMorgan's law again for each of these product terms. So I've applied it once, let's apply it 2 more times. So for the first term, what do I have? I have X gets complemented, and becomes OR, and Y becomes double complemented. And then and remains as is, and on the right hand side, the other term, I have X double complement, or and becomes OR, and then Y complement. Right, so this becomes what? I have X complement or Y ANDed with X or Y complement. And if you go back and take a look at some of your properties, 2 variable properties, you might be able to quickly say that this is the right hand side, but we don't have to do that. We can distribute it to check. So when I use foil here, I'm going to get X and X complement and Y complement, X and Y, order doesn't matter, Y and Y complement. So this tells me that this goes to 0, this goes to 0, and I have X complement and Y complement, or X and Z. X and Y, right? So this is my right hand side. And actually, let me put this in blue. What can I put this in blue? I can say this guy is X exclusive or Y complemented, and this is exclusive NOR. So they both should be the same, which we have proved that they are. So whenever you see, very, overall things getting complemented, something like this, the entire expression gets complemented, for example, that actually, indicates that you can leverage DeMorgan's law to simplify pretty easily. All right. So let's see, we did A, we did B, let's do C. For this, I need to copy because I'm not going to remember this. And this goes down to 2 literals. And add a page here after. All right. So what are we doing? We are doing this. We are simplifying down to 2 literals. And their laws with exclusive OR instead of just OR, not and. Are there laws with exclusive OR and exclusive NOR? No, there are no laws directly with exclusive OR. The problem is this, right? The problem is exclusive OR and exclusive NOR logic functions are actually not, logic functions like NAND and. They are derived from AND, OR, and NOT. So it's just a compact representation of those basic gates in order to check for equality or inequality. So that's the reason why there are no laws directly for exclusive OR and exclusive NOR. All right, let's see. Okay, so let's start with this example here, which is our last one, C. And I'm feeling pretty good about this because there is an X here, there is an X here, there is an X here, and there is an X here, right? So those four terms right away, I know that they are going to give me a pretty simple answer there. What is that going to be? So I'm going to combine the first, second, and the last two terms by pulling out the factor X from them. Yes, exactly. It's going to result in X. So 1 or Y and Z or W complement, right? So all of that is going to go to 1. And then from the second and the third term, what do I have? Let's try to see this. I have X complement and Y here, and I have X complement and Y here, right? So in the second, in the terms, in the product terms that are highlighted in blue, those are terms in which there is an X complement and Y, and there is in both. So let's see, X complement Y in both. So I'm going to get Z for one and 1 for the other. Do we have to show work this step, or can we just jump on homework and test? So the more work you show, the better it's going to be, especially for the tests. And when it comes to exams, the problem statement, I'm going to explicitly tell you whether you need to mention the property name, mention the property number or not. But in general, as far as Boolean algebra simplification is concerned, please show please show your work in detail. That way the graders can follow your steps along. Or if you want to do things in in a very compact manner, then you may want to write a couple of statements to explain your thinking. So that works too. All right, let's come back to this. What do we have? We have all of this going to 1 and all of this going to 1. All right, so what do we have next? I have X, or from the second one, I have X complement and Y. All right, so when you look at this, right, it is very tempting to say that this is the simplest expression, right? It is very tempting. There are two problems here. One, the question said 2 literals, and right now it's 3 literals right now. So that's a problem. The other problem is that this is a direct use of the property, right? Which is, I think, 11D. So if you use 11D here, what do you have? X or X complement Y simply goes to X or Y. So I can actually go back to 11D and show you whether the thing is same or not. Where did we do this? We did this over here, right? So it looks like in our case, in our proof, we have X and Y switched, right? But that's fine. X and Y switched doesn't really matter. We are just doing an OR operation between them. So here is the involution, the 11D property, X and Y complement or Y, right? It simplifies to X or Y. That's exactly what we have used over here to do that last step right there. X and Y were just switched. So let me just point that out. This was 11D, because that's not very clear, but that's not very easy to see. What I found in my experience is a lot of these things are pretty easy to identify with practice. But this one, right, the use of 11D it tends to be the most kind of difficult for students to identify. So just want to point that out over there. Okay, so we have done these 3 problems, and in the slides, those 3 problems have still been solved and their properties have been listed on the right. So you guys, if you need to look at things step by step with the properties, you can take a look at those. Also, the steps on the slides might be slightly different from the way I did them, right? So the sequence of the properties used might be different. Goes to show that there are many ways of going about a Boolean simplification problem or verification. Right, so that's A, that's B, and that's C. A couple of options for C. All right. Now let's take a look at DeMorgan's law in terms of symbols. So we are coming to kind of the fun part of DeMorgan's law and the concept of pushing bubbles around. And this is fun mainly because it is a manipulation of logic diagrams as opposed to logic expressions, right? So it'll boil down to adding bubbles and canceling bubbles and moving bubbles and pushing bubbles. So it's very graphical, and so I think that it's going to be a little bit more fun than dealing with things in a logic expression form. So what do we have here at the top? We have an AND OR circuit, right? So why am I calling this an AND OR circuit? Well, I'm calling this AND OR because my first level is AND, my second level is OR, right? So let me just highlight those levels. This is level 1. Right? All those logic gates are functioning at the same time to evaluate the outputs at these intermediate points as they relate to all the inputs, right? So all of these are happening at the same time. So that's my level 1, which is my AND level. The next level is my OR level. So this is a 2-level AND OR circuit, which is, generally or often called a sum of products logic diagram. So this is in its SOP form, sum of products form, SOP, right? You do product, and you can have several AND gates, right? Doesn't have to be 2. You can have 10 AND gates over here in level 1. Those will be your products. And then after you compute your products in level 1, you do a level 2 sum or OR, right? So that's a SOP form. Now, so AND OR circuit in some literature, SOP in some other literature. We are going to mainly stick to the SOP form, SOP nomenclature. Now, let's try to look at, can we take this SOP logic diagram and convert this into a NAND only implementation? As you can see, the last step here is a NAND only synthesis. You see this? This is the same logic function as this with some arbitrary inputs and outputs. Doesn't matter. All those inputs are here, that output is there. Doesn't matter whether we call them or not. But the claim here is this function is the same as this function, is the same as this function, and the attractive aspect of the last one is it only uses NAND gates. Now let's make this a little bit more general. Any sum of products expression can be converted into a NAND only synthesis. Let's make it even more general. Any logic function can be synthesized using only NAND gates. What is the benefit of that? Well, fewer transistors, right? We know that if I use AND and OR, I'm going to have a lot more transistors, a lot more propagation delay than if I just invest in NAND gates. So it's going to be cheaper in terms of propagation delay, it's in terms of real estate. In every which way, it's going to be cheaper. And, suppose you were trying to implement this not with an FPGA but with discrete ICs, if you do this, you just have to purchase NAND gates. But if you do this, you have to purchase AND gates, you have to purchase OR gates, and you may also have to purchase NOT gates as well, right? So a lot more expensive, and it's kind of a lose-lose situation if you choose to do things in a SOP form. You got it. So if there is a NAND only synthesis, there's also a NOR only synthesis, right? So NAND and NOR, because of this, are called universal gates, right? So NAND comma NOR are called universal gates. Because I can take any logic expression and just use NAND gates to do it, to synthesize it. And I can take any logic function and use NOR gates to implement it. So would there be a benefit to using both NAND and NOR gates? So I'm not even talking about both NAND and NOR. I'm talking about just NAND or just NOR, right? So I can do everything with NAND and I can do everything with NOR. They are both sort of identical in terms of the number of transistors, the propagation delay, the size it takes, right? The real estate it would occupy. But not that beneficial to use both, right? So you would not use both. You would just use NAND, or you would just use NOR. Now it comes down to the preference of the designer, whether you want to do it just using NAND or just using NOR. But the point is to use only one type of gate, NAND or NOR. Now let's go through this here. How did we go from here all the way here? What did we do? We added bubbles to the circuit. Let's do this graphically. So when I add a bubble, what does that mean? That means inversion, right? But I cannot just invert things once. That will change the logic function. I have to do it twice. So I can do things like this, 1 and 2, right? Everything else is the same. That will be fine. And now this is not particularly useful. So what I can do is I can move this guy on this wire over here, and I can move this guy on this wire over here to get this. And similarly, I can do for the other input, one bubble there, one bubble there. Because I've added two bubbles on the same wire, I've kind of complemented them twice logically, which should not change the logic function at all, right? So that's how I got that bubble there, right? Now, if you notice, this has become a 2-input NAND gate. This has become a 2-input NAND gate. And based on DeMorgan's law, this is also a 2-input NAND gate. Let me draw that. So we started with the AND OR circuit and we ended up with NAND only synthesis. Now, one thing that you don't see in this particular slide is a NOT gate, right? So we'll try to do some interesting examples and try to see if we can synthesize any, even a NOT gate with a NAND gate or NOR gate. So what I'll do is I will add a slide here because I want to talk about synthesis of logic functions. How are you synthesizing logic functions, right? So you have an objective, you have the truth table. I want to express those logic functions in terms of their logic diagrams, right? So I want to get that logic synthesis going, logic function synthesized. The difference between synthesis and implementation is once you have synthesized it, you actually have to implement it using hardware, right? So that's the difference between your synthesis step and the implementation step. Now, synthesis, I'm talking about symbols, let's take a look. One way of doing it would be basic gates. And I will have to use AND, OR, and NOT. Right? So I can synthesize any logic function using basic gates, but I'll need 3 of them. The second one is use universal gates. NAND and NOR. Right? So I can just use NAND only, or I can just use NOR only, and you should be able to synthesize any logic function. So let me just add that here. Any. And we'll keep adding to this list actually. As we go on through the lectures in this course, we will keep adding on to this list. We'll try to see whether we can use other components to synthesize logic functions, and the goal will be one component, any logic function. Can we do it or not? Right? And the short answer is yes. There are many others that are on this list. Okay, so let's come back here. We did this. Now what do I want to do? I want to get into representing the symbols, DeMorgan symbols for OR, NOR, AND, NAND, buffer, and inverter. Now, all of these are symbols, and on the right we are also writing the equivalent expressions, right? So the claim, what are the claims here? The claim is an OR gate is the same as invert the inputs first, go through an AND gate, and then invert the output. Where is that coming from? Well, it is coming from DeMorgan's law. You see this? On the left hand side you have X or Y. So if you go back to DeMorgan's law, what does that mean? It is X nor Y equals X complement and Y complement. Now if you were to complement both the sides again, what would you get? You would simply get X or Y, which is your symbol here. But on the right side, what do you have? You have X complement and Y complement, and the entire thing is also complemented, right? So if I use color code here, yellow for this guy, blue for this guy, and let's say I have pink for that guy, which is the same as X or Y. And now you can actually go down this list and take a look at, okay, if the second one is sort of straightforward because it is DeMorgan's law directly, right? It is before we did the complement on both sides. But the point is, you are able to take any one of these logic functions and be able to synthesize it using NAND only or NOR only. What it'll boil down to is, where are you adding those bubbles? Are you adding the bubbles at the input side of a gate, or are you adding bubbles to the output side of a gate? And the second thing that you have to be careful of is, you cannot just add one bubble. You have to add 2 bubbles. One to manipulate, the second one to actually make sure that the logic function stays consistent, right? So we'll do a lot of examples here to kind of look at these variations of the symbols, but they are given over here as a list. So the best way to actually understand the underlying concept is to go through some examples. So we'll do that over here now after this. Now, first question, can I synthesize a NOT gate using NAND? Right, we'll try to ask the question, can I synthesize NOT gate using NAND? Excellent. Right. Yes. All right, so let's try to see what is the symbol of the NOT gate. We have this guy going in and you have NOT coming out, right? So if X goes in, X complement comes out. That's your NOT function. Now, how would you express that in terms of, say, what would happen if you ANDed X, right? So with X itself. So let's say X equals x and x. Can I say that? X and x is x, right? This is one of the properties that we saw before. So this should be okay. Now what happens when I complement both sides? When I complement both sides, it should not change logically, right? It should be consistent because I'm doing it on both sides. So I started with a property from Boolean algebra that we have proved, which is x equals x and x. And then I complement both sides. Once I did that, on the left-hand side, I had a not operation. On the right-hand side, I had, just as the Alex pointed out, x, Nand, x. So if I wanted to draw the symbol for this looks like this guy. And for this guy, it would be a 2-input NAND gate where both the inputs are tied together to the same x. So the claim is, yes, you can. A NOT gate is the same as taking the variable you want to complement and providing the same variable at the input side of the NAND gate. And that's how you get a NOT function. All right, let's try to do this. We can do maybe the second question, which is NOR. So let me copy this and say, can I do this for NOR? What do you guys think? All right, brilliant. All right, so let's see. Here, the property I'm going to start with is x equals x or x. Then I'm going to complement both sides. On the left-hand side, I have a NOT operation. And on the right-hand side, I have an OR operation between the same inputs. Right. So this is consistent with what you want to achieve. You want to be able to achieve synthesis of a logic function using just NAND gates, right? So we are able to do that for NOT, for just using with NAND, and we are also able to synthesize a NOT by using a NOR gate. I am not. Let's see. Let's do some examples here. I want to take a after, yeah. All right. So maybe I can take an example. Here I have an AND function. Now I have an OR function. And then maybe I can invert this. Then I can go into an OR function. I'm just, drawing some logic function here. Let's call this A, B, C, and D. Maybe even change this to a NOT first and then go into that. And then at the end, I'll call this F, right? So I have some logic function, right? And it is not in the SOP form. It is not even in the POS form. It is some, right? It's not doing something that is consistent with AND OR circuit or AND circuit, SOP or POS. It doesn't have one of those forms. Now my goal is to convert this into, I don't know, NAND only, right? So let's say our question is convert this into NAND only. Convert this into NAND only. Synthesis. So let's go in and try to convert this into NAND only, and the intermediate steps I will do are in blue, for example. So just to identify them, I will call them gate number 1, 2, 3, and then 4 and 5. Sure. Now, the question is very clear, right? Convert this into NAND only. Right now, it has all the basic gates, and or not. Where should I put the bubble as far as gate number 1 is concerned? Before a gate, do you normally just put a bubble? So here, about that inverter at the gate, right? So the input of the gate. Most ICs already provide inputs in their true form and complemented form. So sometimes you may not even need this, right? So the inversion operation is just provided as an additional input in most situations. But you are correct to point out that this could be represented as a NOT gate. This is just a representation, right? So this is just a graphical method of drawing things out. It could be this way, or it could be a bubble. Either one will work, right? Because we know the bubble signifies inversion. So if I do that, or if I just put a bubble over here, they should be the same instead of the NOT gate. But I want to point out that most ICs have inputs available to it in true form as well as complemented form. So in a lot of situations, you don't even have to invert the inputs directly, like A, B, C, D, because they're already available. All right, so let's go back to our question. Convert this into NAND only. Where should I put the bubble as far as gate number 1 is concerned? I want to convert this into NAND only, right? So where should I put the bubble for the first guy? On the output. Okay, on the output is correct, right? So because if I put it on the output right here, this guy has become a NAND gate. So that's what we want to do, right? We want to convert this into NAND only synthesis, right? So I've added the bubble to the output side of the AND gate. That's good. But I cannot just add one bubble. I have to add another bubble, right? Because that would be logically changing this. So I'll add another bubble right here. But this guy, you can see, I don't like just this guy to have one input bubble. I want to have another bubble over here, right? Because once I do that, once I add another bubble here, this guy will become NAND, right? So I'll add one more bubble here as my second step. And again, I cannot just add one, I need to add two. So I've added it there and I've added it there. My step 1 is highlighted in yellow. My step 2 is highlighted in blue. What should I do with as far as this is concerned? Should I add at the input? Should I add at the right? I'm going to remove 5 at the end. Sure, that's one of the good things that happened here. How about 2? Where should I add the bubble? Input, output, D, right, D, the input. So my next step is input here and input here, right? Once I add those two bubbles, they are logically going to change things. So I need to add 2 more. You see that? Now, let's zoom out here and take a look at where we are. I'm going to use maybe green to identify that I have a NAND. This is a NAND. I'm good with that. This is a NAND. I'm good with that. This is a NAND. I'm good with that. This has cancelled out. This has cancelled out. The only thing remaining is over there. Right? So let's go ahead and draw the answer here. I've got A and B. Draw it in red. Going into a NAND gate. the output of that NAND gate goes to an input of another NAND gate. And I have one more NAND gate over here, which is driving this guy. The first input goes straight through, and the second input requires an inversion, right? So what is an inversion? I need to use a NAND. So what I'm going to do is I'm going to use another NAND gate here with both inputs tied together, because that's what gives me a NOT, and I'm going to get into the next one. So this is my A, B, C, D, and F. You guys see that? So hopefully this example kind of helps you see two things. No matter what kind of logic diagram you start off with, you can always add bubbles to manipulate it to convert it into NAND only or NAND only synthesis. Does NAND only hurt speed? No, it improves it, right? So for NAND, because there are fewer transistors, the propagation delay through a NAND gate is going to be smaller than, for example, one of the basic gates for the same number of inputs. So it's a win-win, right? If you go to NAND only, it's a win-win. Like there's nothing that we are losing here. Which is why you tend to do things just using NAND or just using NOR. So NOT needs 2 transistors, NAND needs 4, right? But so if you average it out, are you going to see a lot of NOT operations happening? Probably not. You will most likely see a lot of AND operations happening and an OR operations happening, right? So sure, you can have some special cases such as the NOT, but in general, if you look at logic functions, they will have a lot more AND and OR operations going on rather than NOT operations. Even the same propagation delay as an inverter. So here, it's not just about the number of transistors. It's also about how they are placed, right? So if it is cascaded one after the other, something like what we did for NAND and AND, that changes things, right? Like that's a significant change. But if every inverter, if every transistor is functioning at the same time in parallel, then it doesn't matter how many you have. If size might be different, but just in terms of propagation delay, it might not matter that much. All right, so all right, let me come back to this. With this example, I wanted to convey two things. One is, no matter what kind of logic diagram you start with, either in SOP form, POS form, some arbitrary form that is not one of those nice SOP POS, you can convert things to NAND only. You can convert things to NOR only. The difference is, as you are adding bubbles and pushing bubbles through, you need to be careful about where are you going to add the bubble, at the output side or at the input side. Your overall design goal will dictate whether you add things to the output or whether you add things to the input or not. And as you are adding those bubbles, some of these kind of situations will happen. You may actually cancel out the NOT gate. And in some other situations, you may not be able to, in which case you will have to synthesize the NOT operation using NAND only or NOR only. But no matter what you do, as long as you are adding bubbles and pushing bubbles and all that, you got to do it 2 at a time, right? Because you cannot change the logic function. the logic function at every place needs to be consistent. So I cannot just add one, I need to add two bubbles. Questions about this example? All right, let's do another one. Convert AND gate to its NOR only synthesis. Say two input NAND, two input AND will do it. Two input case, two input AND gate. So I've got a two input AND gate. I'm going to draw the symbol here. Let me name these guys, say A, B, and C. Sure. Now I need to convert this into a NOR only synthesis. So at the end, I need to have a NOR only logic diagram. So where should I add the bubbles? Inputs. Because if I did it on the outputs, I would actually get a NAND only synthesis, right? So I'm not going to do it at the output, I'm going to do it at the input. Should I do it for one input or both inputs? Both, right? So I have to do it on both so that I can use DeMorgan's law. So I'm going to do 1 and 1. Okay. Can I just add these two bubbles and will I be okay? Or should I do a few more things here? I need to also add two more bubbles to the same wire to cancel that out, right? Which is essentially my NOT gate. So let me just draw the symbol here. So you see, I added these two bubbles so that I can convert this into NOR gate. And then I added these two NOT gates so as to cancel my inversion, right? So what does that look like? I've got A going into a NOT gate, which is a two input or a NOR in which both the inputs are the same. And B does the same. That's how I'm getting my NOT functions. And all of that goes into another NOR. This is my A, this is my B, this is my C. This guy maps to that. This guy maps to that. And then this guy maps to that. Can I see that? We are having a emoji smiley competition here. All right. Oh, now I see it. I see that. All right. It was smiling though. You guys all did right. So knives is all right. Questions about this example? We took an AND gate and we converted it into a NOR only synthesis. Again, things that need to be you need to be careful of as you're doing this. Where should I add the bubbles? At the input side or at the output side? Well, it depends on where you're trying to go. If you're trying to go for NOR only, if you start off with the AND gate, you need to add bubbles at the input side. You cannot add just one bubble at a time. You need to add two bubbles so as to logically be consistent. All right. Questions about this, guys? Yes, absolutely. It's NAND is more efficient here. But that would have been a simpler example to work on. That's why I didn't do it, because it would be just one bubble and a inversion, right? So you would go NAND and then NOT. So it would have been a simpler example. I wanted to do something a little bit more interesting. That's why I chose a NOR only synthesis as the question. All right. So it would be a 2-input NAND into a 1-input NAND. Oh, no. So it would be a 2-input NAND into a 2-input NAND, but for the second NAND, both the inputs are tied together. Right? So it would be something like this. And you would get a NAND, but you would also get another NAND. But for the second guy, both the inputs are tied together. Time for exclusive OR. Yes. So that would have been, the answer for the NAND only synthesis. All right, let's see. We are going to try to look at exclusive OR, and we'll try to see if we can synthesize the exclusive OR function using NAND gates only. And we actually, should be okay, because the claim that I laid out earlier was, you give me any logic function and I can synthesize using NAND only or NOR only. And exclusive OR is, it's a pretty simple logic function, and we should be able to do this pretty easily by pushing bubbles through. So again, the same manipulations that we have been talking about. So let's try to take a look at this graphically, right? So we are going to start off with their AND OR gate diagram, or their sum of products logic diagram. We have X and Y going into two gates. Both of these are AND gates, but one of the inputs is inverted, right? So we have over here, we have X complement and Y, and over here we have X and Y complement. And at the end, we have the OR operation giving us the exclusive OR function. So let's try to see if we can push bubbles through and get this done for exclusive OR, right? So I have this exclusive OR function over here. What I'm going to do is manipulate the output of the NAND and the input of the OR here. So step 1, add this and this. Step 2, add this, right? I'm adding two bubbles on the same wire, so logically I'm consistent. And I'm adding things to the output of the NAND gate and the input of the OR gate, so that eventually I get everything to go to NAND. And as you can see, I've got a NAND here, I've got a NAND here, right? So gate number 1, gate number 1, gate number 2, gate number 2, and gate number 3 has become gate number 3 here. All of them are NAND, except over here I need an inversion for X and for Y. Now in some scenarios, like I said, X and Y, because they're inputs, you may have true form and complemented forms available to you, so you may not need to invert the inputs. And in some other cases, only when explicitly mentioned, you may have to do this inversion yourself, which means you have to have a NOT gate, which means you need to use two more two input NAND gates with both inputs tied together instead of this guy and this guy. So that depends on how the problem is stated. But that's essentially your exclusive OR operation being synthesized using NAND gates. And you could have done that even for NOR gates, except things would have been different. Over here, you would have been adding, if you were going for NOR only, you would have added bubbles to the input side and cancelled them to keep things consistent. And for this guy, you would have added things to the output side and added more to keep things consistent. Right? So it's just about figuring out whether you're adding bubbles to the input side or output side of each logic gate, depending on how you want your answer to look as. All right. Now we come to this combinational analysis. This is some logic diagram. It has three inputs, X, Y, and Z. And the question is, what is its functionality? Now, there are several things you can do with this. Like this opens up the conversation to, what are the different ways to express a logic function. We have been seeing a truth table, a logic expression. This is represented using a logic diagram. So there's a lot we can do with this particular logic diagram that is given to us. The first thing that we'll do is talk about this word, combinational, right? So what is combinational analysis? And the opposite is sequential analysis, right? So what is the difference here? Well, combinational analysis doesn't have any memory. No memory. I'd build the expression first. Bingo! That's brilliant. Yes. You would build the expression first, and that's exactly what we are trying to do here. So let's come back to this. The definition of combinational analysis is this. Let's see, combinational circuits. I'm going to define combinational circuits here. Let's circuits where output or outputs, right? We could have multiple. Outputs depend on the combination of present inputs. No memory. Will we ever have feedback? Absolutely. That's how we get sequential circuits. So we are looking at, the moment we start seeing feedback, right? That's when you're looking at, things with memory. Those will start with latches, flip-flops, registers, counters. All of those will have feedback. So we are going to spend, several weeks talking about those ideas. So yeah, that's coming up. Right now, we don't have any feedback. Things are only moving in one direction, input to the output side. So for now, there's no memory. But when we do get that, it is. It is, and at times it's counterintuitive, which keeps things interesting. The opposite of combinational analysis is this. Counterpart is sequential analysis or sequential circuits. So for sequential circuits, your present outputs, your current outputs would depend not only on the present inputs, but they will also depend on sequence of past inputs, giving it the name sequential circuits. Right now we are in combinational world. Things are only moving in this direction. Inputs to the output. Outputs depend only on the combination of the present inputs, hence the name combinational analysis. So let's come back to this. What is its functionality? Student X says there's some student, and I usually use two students, student X and student Y. Student X tends to do things in not so elegant manner, and most often, very often, he is wrong. Student Y tends to do it in a more of a proper manner. So student X and student Y, that's going to be kind of our, you will see me refer to these two students several times. So student X says, you know what, I'm going to actually use a table here. I will build it up with X, Y, and Z, and I will have F for the output column. And for each entry here, 0, 0, 0, 0, 0, 1, and so on, all the way to 1, 1, 1, I will try to figure out what happens to F by tracking these inputs through to the output. For each condition, I will try to do this, right? That's student X that's trying to do this. Student Y says, no, that's not going to be efficient way of doing things. You're spending unnecessary time on this. It's not elegant. It's not the way to go. Instead, do this. Let me maybe do it in red. Instead, write the logic expression from input all the way to the output. So let's try to do it here. Let's try to do it here. Let's try to do it here. What else do I need? And then eventually for F. So for the first one, what do I have? I have X going into an OR gate with Y complement. Right? That's my first intermediate result. The second one is X complement Y and Z complement. And then over here, what do I have? X or Y complement ended with Z. And at the end here, F is simply the OR of the last two, right? So let me just write that in blue here. At the end, F is X or Y complement ended with Z. And there is a OR with X complement and Y and Z complement. All right. So that's done, right? I've got the logic expression for the output F. Now what we can do is we can now take this guy and try to fill up the truth table for this. And I'll tell you guys how to do this in a slightly quicker manner. So this is the logic expression for F from before. And I'm going to build a truth table here. And I will just have X, Y, and Z in that order, and then F over there, right? So I've got what? 0, 1, 0, 1, 0, 1, 0, 1, and then 2 zeros, 2 ones, 2 zeros, and 2 ones, and then 4 zeros and 4 ones. So that's the complete table I have. Should we simplify first if possible? Right now I'm just not even looking for simplification. Sure, you could, and my guess is you will be able to simplify it a little bit, but right now it's unnecessary because I'm trying to find its functionality using a truth table. So my goal is to fill up the truth table. We talked about how to do it in a bad way. Now we are talking about how to do it in a good way, right? So let's try to take a look at this. Where should I put the ones? I'll only look at where am I going to put the ones for the F. I will not worry about the zeros because whenever I am done with the ones, all the rest of the outputs are going to be zeros, right? So let's take a look at this term right here. X complement and Y and Z complement, right? So that's what? F is going to be 1 when X is 0, Y is 1, Z is 0. When is that happening? No, sorry, not that. 0, 1, 0. So it's right here. See that? So that will give me a 1 right there. Okay, I am still left with this guy in yellow. Right? What is that going to give me? So let's take a look. I'm going to talk about that over here. I've got X and Z or Y complement and Z. Right? So X has to be 1, Z has to be 1, Y doesn't matter. Y has to be 0, Z has to be 1, X doesn't matter. Let's put it in. Let's highlight them in maybe yellow here and blue here. Now, erase that, and then let's talk about. So x is 1, y is z is 1, right? Where are they? It's right here, and one more spot right there, right? Those are my two yellows. Next, y should be 0, z should be 1, x doesn't matter. Okay, last two columns 0 and 1, so that's right there, and right there, so that's already there. I don't need to write another one again. I'll just put a bubble right there to indicate that. So that's my truth table. The empty spots I'm going to fill with 0, 0, 0, and 0. I'm done. You guys see that? So that would be, doesn't that overlap signify simplification possible? Yes, it does. But since I'm just doing this to fill out a truth table, it doesn't matter whether I write 1, 1 or 1 on top. Like, it's just 1 in that spot. So when x is 1, y is 0, and z is 1, you get a 1 for output f. Right? So that would be a better way to write the truth table. Now, just to deal with this in a different way. So when you said f, right? Let's try to learn some ways to call this. So when you had those two, we literally had this, right? For f, we had x and z, or y complement and z, or x complement and y, or and z complement. So this particular type of expression is called a SOP expression, sum of products expression. The reason is you have got a product, and after you evaluate all those products, you have a sum of all that, right? And you can also call this OR of ANDed terms, right? OR of ANDed terms, sum of products, SOP. That's what that is. Okay, questions about this? Let's try to do another example here. I will talk about how you can convert an SOP to a canonical SOP. So let's say convert sum of products expression to canonical sum of products expression. I'll talk about what that means in just a bit. So when you say what's the function, you just mean get an expression for f. Well, when I say what I meant by what is its functionality, I meant find its truth table. But in general, like I would not do that if it were sort of an assessment, right? So for an assessment, I would provide a little bit more detail. I would say express this particular function using an expression, or a truth table, or a logic diagram, or a timing diagram, or a Nand only synthesis. Like I would be a little bit more specific in terms of which form I want you to represent that logic function in. For now, I was just interested in the truth table. Right, let's see. All right, so I want to convert a sum of product expression to canonical sum of product expression because my goal is to be able to express logic functions in a very, very compact manner. So let's try to do that with another example here. So I'll say f, I'm going to start off with the sum of product expression. I will say x or x complement and y complement, or x and y and z, right? I'll just complement this. So I'm not even going to worry about whether I can simplify this or not, because my goal is actually to convert it into a canonical form. And I'll talk about what canonical means in just a bit. The way you do this is by forcing the terms that are missing, right? So for example, the first term here, first product term here is missing y, and it is also missing z. The second product term is missing z. The third product term is not missing anything, so I don't have to force any literal there. So what would I do? I would start off with f equals x, and I would force y on it, and I would also force z on it. Next, for the second one, I'm going to force y on it. Z on it. For the last one, I'm going to leave it as is because it already has the three inputs, the three variables involved to make this logic function, x, y, and z. Okay, so once that step is completed, I'm going to distribute everything on everything to finally get to my canonical sum of product expression. So let's try to do this quickly here. I'm going to get what? X and y and z, or x and y complement, or x and y and z complement, or x and y complement and z, or x and y complement and z complement, or x complement y complement z, or y complement z complement, or x, y, z. Now are some things duplicates? Because I can get rid of duplicates now. It looks like xyz, there is only one xyz, 110. No, it's just 101 there, right? So I can erase this off. I don't need this. It's already captured in this guy. 100 unique, 001 unique, 000 unique. All right, so now I can write my canonical sum of products expression as, and I'm going to just rearrange it so that they come into this nice numbering scheme. X complement, y complement, z complement, or what should I write next? Should be x, y complement, z complement, I think. Maybe not. I need x to be 0, so that's x complement, y complement, z next, and then is x 0 again? No. How about y? So I've got these two are the last two, 101 and 100, so that's 4. So I got that is good. Then I've got this guy, and then eventually I've got x, y, and z. Sure, and the last one. You guys see that? So I've got x, y, z complement, all of them complemented here from this guy, 001 from this guy, 100 from this guy, 101 from this guy, 110 from here, and then 111 from here. And I've kind of done the final answer here just so that I get into this good sequence of product terms. Those are my min terms. So canonical sum of product is SOP, where each literal is in each sum, in each product. in each product. Yes. So that's essentially your answer. This is your canonical sum of products form. So let me box this up. And this leads us into a lot of things we can discuss here. This is canonical sum of products expression. And this is kind of the long form, right? Everything is, each term is written up in a explicit manner. So this is sort of the long canonical sum of product expression for f. A better way or a more compact way to in that specific order. No, they don't have to be in that specific order. I just put them in that specific order because it is going to help me write the CSoP expression in a compact manner as I show you here. Compact or shorthand form is f, and I'm going to write f is a sum, because sum of products. So sum of min terms. Min terms are 0, 0, 0, 1, 1, 0, 0, 5, 6, and 7. And then it is also very important for me to list the order of the inputs, because if I change the order of the inputs, those numbers will not map to those terms. So what I'm going to do is I'm going to write x, y, and z. That is my specific order, in that order. X is the most significant, z is the least significant. So this is what we call the shorthand way of writing. This is canonical SOP shorthand. Now let's talk about what each of these are. Like this one, right? These are all 1, 2, 3, 4, 6. 1, 2, 3, 4, 5, 6. There are 6 min terms in this. What are min terms? Min terms, let me just put it over here after min term. Min term is a product term in which all variables, all input variables are represented. All input variables are represented either in true form or complemented form. So it's a product. And canonical sum of product, canonical sum of products expression is sum of min terms. So we have got, so those are essentially your definitions of canonical form and the non-canonical form, which we just called SOP. But here we looked at an example where we started off with some expression. We got it into its canonical sum of product form in its long form, right? Everything detailed out explicitly. It had 6 min terms, right? Min term 0 all the way to min term 7, right? Min term 0, min term 1, min term 4, min term 5, min term 6, min term 7. Min term 2, 3 was not part of this expression. So that would be a compact way or shorthand way to represent things in canonical sum of product form. This would be the long form, and this would simply be the SOP form. They're all the same logic function, meaning if you had to fill out a truth table, then you would have the same truth table for F here, and F here. In fact, the last one is going to tell you where the ones are, right? The ones, if you lay out the inputs in that order, X, Y, and Z, the ones are going to be at location 0, 1, 4, 5, 6, and 7. So using this, actually you can write out the truth table as well. X, Y, and Z, and it has to be in that order for that minterm order to stay consistent. This is your F. So this is 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 2 zeros, 2 1s, 2 zeros, 2 1s, and then 4 zeros and 4 1s. Where are the ones? Well, they are at rows 0, 1, 4, 5, 6, and 7. So those are the only places F is a 1, which also means that the remaining places are zeros. So a couple of different forms of going between one to the other. Now when we come back on Friday, we will take a look at product of sums, canonical products of sums, canonical products of sum shorthand. We'll take a look at some alternate representations, and we will take a look at don't care situations, right? So in some situations we have false and some true, right? And for some of the situations, the designers might not care about whether the output is true or false, and we'll talk about that. Those are called don't cares. Let's see. Wait, don't the sums then have to be in a specific order for that to be the case? Yeah, you see, I had to have X, Y, and Z in that same order as I called them here, X, Y, and Z. So if I want to use these numbers 0, 1, 4, 5, 6, and 7, then I have to have X, Y, and Z in that order, right? 0, 0, 0, that's 0. 0, 0, 1, that's your 1. 1, 0, 0, that's your 4. 1, 0, 1, that's your 5. And so on. So absolutely, it has to have that order, and it has to explicitly be mentioned in that shorthand form as well. How did you get minterms 0, 4, 5, 6? So if you see this, look at this guy. When is this true? Well, X has to be a 0 and Y has to be a 0 and Z has to be a 0. Only then I get a 0, right? X has to be a 0, Y has to be a 0, Z has to be a 1. That's how I get 0, 0, 1 or decimal 1. X has to be a 1, Y has to be a 0, Z has to be a 0. So 1, 0, 0. That's how I get a decimal 4. Wouldn't that also be reversed though if you count from... yeah, sure. But so if you go 0, Z, Y, X, you can reverse that order. But what if you go Y, X, Z, right? So it can work for some situations, but not for all the input combinations. The bottom line being, if you want to use numbering scheme, then you have to explicitly talk about the order of the inputs as they appear in the... I'm saying X, Y, Z, 0, 0, 0 in the last row. X, Y, and Z are 1, 1, 1 in the last row. So you have to start from 0, 0, 0. Oh, you mean this order? Oh, no, this can be written in... I just like it to be in this order because it's easier to read.
It'd be easier if I explained.
Yeah,
so if you go back to the other picture.
This one?
Yeah. So you start 0, 0, 0, then 0, 0, 1.
Yeah.
What if you did 1, 1, 1, then 1, 1, 0? Then that would flip the order because that would be the 0th one, right?
No. So I can't have this be mapping to this. So here, let me backtrack here a little bit. The function is this, right? Then I said, in order to convert it to canonical form, I need to force Y and Z here, I need to force Z here, and I don't need to do anything about that. Then I got all of this, right? Now I'm looking at a canonical form that should translate to a truth table, right? So if you take a look at this, if X is 0, Y is 0, and Z is 0, will it give you 0? Yeah, it's indicated by that term right there, right? X complement and Y complement and Z complement is going to refer to that particular entry. And because it is part of my CSoP form, I get a 1 over here, right? But if you
What
look
I'm
at,
saying is
say,
those numbers refer to the rows, right? Like 0, 1, 4, 5, 6, 7 are the rows.
yes, so row.
So if you started counting from 1, 1, 1 down to 0, 0, 0, then the rows would be flipped.
But
Is
I'm
what
saying
I'm
you
saying.
can't. You have to. So here, let me see. What you can do is this. You can reorder things in here. So you could say summation xyz 0, 4, 1, 5, 6, 7. That's fine. However, you cannot change these numbers because they are tied to the order here. You see that? Yeah, so 765410 is fine, but the rows are binary for the number. Yeah. So 000 is that particular row number 0, right? So instead of referring it to each entry as x has to be 0 and y has to be 0 and z has to be 0, I'll just say that is my row 0. Entry. So for 5, sure, but you see 010, right? 010 is what? That term is x complement y and z complement. Well, that is not there in this guy, right? So the function doesn't become 1. All right, good. All right, let's stop here. I'll stop recording.